James Morrill. He's a final year student, also in Oxford, and he's going to talk about neural rough differential equations. And you have your 20 minutes and then 5 minutes of questions.
All right. Okay. Thanks. So, as I said, this is going to be basically a direct evolution from Patrick's talk, and this is an extension of the neural control differential equation method onto the rough differential equation method. Okay, so introduction. So we're going to extend the neural CD approach onto what's called the neural RD approach. And neural RDs are a natural extension of neural control differential equations. And what we'll see is that they actually come into their own, in particular when we have long or very high frequency time series data, because of the way that rough differential equations handle data, make them particularly useful for handling this type of long data that neural CDs or your classic RNNs would generally struggle with. And we'll go on to show experimentally that it comes with a number of key benefits. The important ones being speed, memory usage, and in general improvements of performance compared to neural CDs and other more traditional approaches. So this is just a quick recap of what Patrick's already told you. So we're supposing we have some collection of ordered data indexed by time here, where each X represents an observation of features that exist in RV at discrete time points. And so what we do in the CD formulation is we create a continuous interpolation of the data that we'll denote as capital X. And then the neural control differential equation we can now define in the same way as Patrick did. And so we have this this response variable Y that's driven continuously by our continuous time path X. And this is how, in contrast to an ODE, which is defined uniquely by its initial condition, this is how we get that the temporal data changes to update our solution trajectory. And so the way that these were solved is by changing this DXS. We assume that we can make a differentiable interpolation of the path control of the discrete time data, and then we can evaluate this dx term through its derivative to create an ODE. And this dx/ds is exactly how we get our continuous time evolution involved in the solution of the equation. However, there's a couple of situations when this might become unfeasible. So first of all, there are situations when it's not sensible or not possible to assume differentiability of the path control. And secondly, if we want to see every single one of these data points, then this requires evaluation of the derivative each time we see any data point. And so if we have if we're going to have a very long time series, this requires a lot of evaluations of the derivative and a lot of computations with these integrals, which very time consuming and very memory intensive. So now onto the rough approach. So as Terry explained in this first talk, at a very high level, the ideas behind rough theory shows that the solutions of these equations are not best solved but via point-wise evaluations of the data, and in fact, in a lot of cases, they're doomed to fail. What instead should happen is that we consider these local summarizations of the data over short time intervals, and it's in these summarizations that we can update our solution much more effectively than via these point-wise evaluations. And these summarizations are very specific. They have a specific form, and this form is known as a log signature. I'm not sure if the log signature has been mentioned, but it's basically, you can just think of it as the same thing as the signature of the path. So these are the features over an interval which are most useful for solving these control differential equations. They're exactly the information you need to provide these solutions over intervals. So this is a kind of high-level pictorial description. So the original neural CD formulation is on the left. We have some discretely sampled data. These are the sort of small dots. We interpolate this with a smooth path, and then at each time we see a new piece of data, through its point-wise derivative, we update the neural control differential equation according to the equation as stated before. And then this provides us with an update of our response variable. And so obviously for a very high frequency path, this requires a lot of updates if we want to see every time point. However, the rough approach, what this is saying is, instead of doing this evaluation at every point, we instead look at local intervals of the data. We evaluate these summarizations, and so these summarizations we see as these red blocks here, and these are containing precisely these signature features, and then we actually evolve the differential equation by these summarizations. And this change here is what is turning us from a CD into a rough differential equation. So this is using these rough ideas. And obviously, as you can see, this requires far fewer evaluations of the integral. The effective length of that time series of summarizations is now a lot shorter, which means everything ends up being a lot less memory intensive and also a lot faster to train. And so this is kind of what we're saying here. So the extension is providing a way to solve precisely the same differential equation. The differential equation is not being changed, and what we're solving is not being changed in any way. But these features allow us to take integrals over steps larger than the sampling rate of the data. And so this can be thought of as analogous to a higher order solver for an ODE method. So if we have a higher order solver, we can take a larger step and still retain accuracy. But now we obviously have this added complication that we're not just stepping over time, we're stepping over this multi-dimensional path control. And the log signature and this rough approach is telling you exactly how you incorporate that information to provide this higher order solve over a longer interval, a larger interval. And so the ability to be able to do this has a very, very large practical benefit. So one of the key problems with RNNs that is not solved by the original neural CDE formulation is this thing called the exploding and vanishing gradient problem. And so this is when you have a very long time series, what you have to do is you compute all these forward operations every time you see a piece of data. And then when you get to the end of the time series, you make a prediction, you evaluate that prediction against the true value. But now you have to propagate this information all the way back to the beginning of the series. And what happens is that the gradients involved in that computation, they either blow up and everything becomes unstable, or they vanish and then it becomes impossible to train and learn from this earlier data. And so being able to take these larger steps means that the effective length of the time series that we have to backpropagate through is a lot shorter, and therefore it helps significantly mitigate this problem that starts to become a very real issue with time series of length around 500 in general, which is not very long for a lot of high frequency problems. And so these are the three key reasons why these large time steps in this rough approach is particularly effective, and it's in the reduction of the impact of this exploding vanishing gradient problem. It simultaneously reduces training times and reduces memory requirements, the memory requirements due to storing of these computations in the forward pass along the length of the time series. So how do we actually do this? Well, there's a tool from rough analysis called the log ODE method, which states that the solution of this equation here, a CD equation, can be approximated by this now ordinary differential equation, where the ordinary differential equation has this log signature term. And so this log signature term is giving us the information about the path control that we need to be able to perform this equivalent solve, but through an ordinary differential equation. And apologies for formatting, but this becomes exact as n tends towards infinity. And so this might look a bit clearer when I compare it to the CD approach. So the rough approach is solving the equation via this ordinary differential equation. And we can see that this differs from the CD approach as outlined by Patrick by the replacement of this derivative evaluation function, dxds, by this log signature term. And so the log signature is it's playing a similar role to the derivative in that it's extracting the information about the multi-dimensional path control that we need to solve this equation. But it's actually it's actually a much richer set of information. The derivative obviously just contains the derivative. The log signature contains sort of effectively, to an extent, the derivative at first order, but it also contains these second, third, and fourth, and higher order terms depending on how high we truncate n. And crucially, this information is what's most important for solving these CD equations. So this is precisely what it is. The signature comes out of looking at how you solve these CD equations and extracting the information that is most relevant to the solution. And so just as a bit of a big recap overview, so we started by wanting to solve this control differential equation. As Patrick showed, this could be achieved via using this derivative formulation with a piecewise derivative path. And then we introduced the rough approach. And so this derivative is replaced by the log signature. And so the star here is just denoting the dependence on the choice of intervals, which we're free to choose. And so the log signature is evaluated over different intervals that will depend on the problem, depending on how fast the path is changing in any local region. And so this is another high-level pictorial representation showing a similar thing to the previous one. But this here represents the original approach. So we had some discrete data, these green dots at the bottom. We compute a continuous time path, and then we update the equation at all these orange integration steps to evolve our hidden state. And so there's a lot of steps. But in the rough approach, as in this equation on the right, we do the same thing. We formulate a continuous time path, but now where these curly brackets are, these are our local intervals. We compute the log signature over these local intervals. And then we end up with a log signature path, which is a lot more slowly varying, and it requires far fewer integration steps to actually resolve. So neural CDs, a comparison between the two, and when should we use which one? So to an extent, they're sort of the same thing, but we find that the CD formulation and the derivative formulation, it tends to work very well on short time series problems. Anything less than about 500 time points performs very well, tend to not see an issue. And the log signature seems to offer not very much practical benefit, at least in the examples we've tried. However, for anything longer than this, it's absolutely essential that we consider this problem using the rough approach, because the neural CDE, for the reasons I mentioned before, with regards to the exploding gradient problem, memory requirements, and training time, it starts to break down and training becomes basically impossible in log cases. And so, I'm okay. So this is just some examples on a few experiments we tried. So this is a classification task for a problem that has a sample length of over 7,000, so 17,000. So this one's nearly 18,000 in fact. And so what each of the features represent here is some indication of the movement of a particular species of roundworm, and the goal of the task is to classify the worm as a wild type or a mutant type. And so you can see an example of the data on the right. So it's quite rapidly changing. It's sort of almost rough path-like in a sense. And so this makes it seem like, well, this would be a particularly good problem to try the formulation on. And so here are the results. So we've tested it against the original neural CDE formulation, and another benchmark, an ODE RNN, which is another typical sort of industry standard ODE method, where we have, in the ODE RNN, we've actually, when we've taken larger steps, we've pushed that time series dimension into the channel dimension of the ODE RNN. I'm not sure how much sense that makes, but basically the ODE RNN is given an opportunity to see every piece of data. And as you can see, the ODE RNN, the accuracy over a range of step size, it basically fails to train. The neural CDE is a decent amount better, but compared to the rough approach, when we include these log signature terms, the rough approach is head and shoulders above the rest. And so you can see that taking the best performer here is actually taking a log signature features of depth 2 at step 4, where it achieves 84% accuracy. And it's compared to doing, as you can see, compared to doing the neural CDE model with a step size of 1, which takes nearly a day to train, the top performing rough model takes under 3 hours to train. And it still achieves decent performance comparatively at much larger step sizes where time and memory requirements are a fraction even of this. And so for a second problem, really 3 problems in one, the aim is to predict a person's respiratory rate, heart rate, and oxygen saturation, so some of their vital signs, from observed PPG and ECG data. So PPG data is a measure of sort of blood volume pulse, is another word for it, and ECG data is classic heart rate information. And so this data was sampled at 125 hertz, and each sample has a total length of 4,000 time points. And so I apologize for the large table, but basically the story to take away here is that the bold values represent the best performers for a given step size, and you can see the neural differential equation, in this case, the depth 3 model, is significantly better than any of the other performers at reduced time and reduced, at reduced time and reduced memory requirements, in the sense that at a step size of 512, it actually, the best of performance is actually achieved. And this is giving us an indication of what that trade-off is between the length of the series, the length of the effective series that we need to be considering, and the size of the intervals through which the log signature can efficiently extract the useful information from. So this hopefully will be a little bit clearer. So these are the heat maps of loss against the true values for the neural rough differential equation method. And so red is good, so the deepest red region is the best performing. And so what you see is, so if we look at the top left, the top row is the depth 1, second row is depth 2, third row is depth 3. And so we see that by including this rough methodology, the best performer is actually, it shifted both away from a step size of 1, and it shifted down in depth. So there is a trade-off where at some point there is a step size at which the log signature can efficiently represent that information, and also the time series is not too long that we have these problems with exploding and vanishing gradients. And so about finding this region, this in practice ends up being found by hyperparameters, a hyperparameter search. And so we'll evaluate a range of step sizes in different depths, and we find the optimal ones, the optimal matching ones that give you best performance. And so just to sum up, so here we introduced the neural rough differential equation, which is an extension of the neural CDE framework. And we showed how ideas from rough theory can be used to reduce the effective length of a time series while still solving the same underlying differential equation. And finally, we demonstrated that using this approach on long time series really does generate improved performance across a range of predictive tasks. We get significant speed ups and reductions in memory reusage compared to what would otherwise be a naive implementation of neural CDEs or an RNN. And that's everything. So thank you very much for listening.
All right. Thanks a lot, James. Are there any questions or comments?
I have a question for James. Hi, James.
Hello.
Hi. So if you have a time series that is like oscillatory, very oscillatory somewhere, and maybe it's smoother on some other parts, I would say that you would sort of need different time intervals over which you summarize the information with the log signature, and different variable steps in some sense, and not using always 512 steps or 256 and so on. Is it possible to do variable step size stuff with neural CDs, neural rough Ds?
Yeah, so in theory, it's definitely possible. So you end up creating a neural ordinary differential equation with a log signature term, and so you can have adaptive error monitoring on that ordinary differential equation. And so in theory, when you can use these error monitoring schemes to reduce or increase the size of your step, given how rough the equation, the time series is at that point. As to an actual implementation and a proof that this works effectively, not quite there yet.
Okay, thank you.
Any other questions?
I think there's one question come up.
Oh yeah, there's one in the chat. So a question by Bo is whether speech is a good data domain to apply this to, because he says the original neural CDE paper did it on speech comments.
So my knowledge of speech data is relatively little. So I know Patrick evaluated the speech comments data using neural control differential equations to great success, and they perform really well. But it depends a lot on what features you put in. So there are transformations. So I think you end up computing Mel frequency coefficients of speech, and then you evaluate how this performs on top. And so long as the features you put in terms of raw waveforms, I reckon you'd struggle. I haven't actually tested it, but I assume without feature extraction on or some more specialized features put in the neural CD, there's nothing specific about the neural CD that would make it particularly good at untangling speech data. And so I would definitely recommend you do some more standard speech pre-processing before you try it.
All right.
There's two more questions in the Q&A.
So Remy is asking if you've tried different type of interpolations on your data points before computing the log signature. So instead of, I guess, piecewise linear, do something else. Yeah, so interesting you ask. We're actually doing lots of tests on interpolation schemes at the moment. So there's your standard linear interpolation, and so then there's the natural cubic spline interpolation, which has the advantage of being differentiable, which means that these adaptive schemes work much nicer and they run with far fewer function evaluations. And so we've also looked at, we're also looking at rectilinear interpolations where the values stay constant unless there is actually a new piece of data, in which case we have over some epsilon time, everything jumps up. And this has the advantage of being causal, which a linear interpolation is not. And so there are a few things, and I think on Torch CD in the library, Patrick has written an explanation about different interpolation schemes and which to use when. So it's probably best going over there if you want to look. All right, and then let's say this is the final question by Linky. It's sort of a follow-up on Chris' question, and sort of wants to know more about how it deals with irregularly sampled data and exactly how the high frequency of measurements, sort of how you have to adapt the methods if there are periods of high frequency and low frequency sampling. Well, so this is one of the really nice things about CDEs, is that they don't really care about whether or not your data is sampled or regularly sampled, is regularly sampled or irregularly sampled. As with the signature, if the data is irregularly sampled, well, the signature is still perfectly well defined on the
underlying continuous path. And so you compute the signature, you leave the data as it is. You don't have to do any interpolation, interpolation of missing values. And in principle, this irregularly sampled is now on the same footing as regularly sampled data, and all these methods work without any real change to your inputs.
Actually, if I can jump in quickly, can you hear me?
Yep.
Yeah, yeah, just extending just off of what James has said. One of the nice things about this is that because you're solving a differential equation sort of in continuous time, then actually your amount of computational effort that goes in, you can manage through the differential equation solvers, which automatically adapt to the complexity of the incoming input. So what this means is if I give you some, incredibly finely sampled sequence over 1 second, but it's been sampled at like 1 billion hertz, right, which is clearly ridiculously overkill, then the methods we've been describing here just automatically adapt to the complexity of that input, rather than say something like a recurrent neural network, which kind of mandates that it take in every little input one after the other, despite that being obviously hugely unnecessary.
All right, thanks. So I think, both James and Patrick, they will be around for the breakout session. And now it's on to Peter Foster from the Turing Institute. Don't worry, Peter, you'll have your full 20 minutes, although we're starting a little bit late. And